Hello all, welcome to the SSCA webinar series. Today we have our speaker Arghya Das. His current paper titled Semi-supervised feature selection using maximal mutual information and minimum correlation through augmented learning is being accepted in statistics and application and will be published soon in the forthcoming issue of the journal, volume number 24, issue 1. So congratulations, Olho, and without any further delay, please start.
Thank you, sir. Good evening, all. So, this paper is about semi-supervised version of feature selection, and here we are using maximum mutual information, and we are also using the concept of correlation, and together we are creating a concept of augmented learning. Okay, and this work has been helped by Dr. Saptarsi Goswami sir, Professor Amlan Chakraborty sir, and Basabi Chakraborty ma'am. Just a small introduction. As in recent times, we are getting a plethora of data sets due to the social media. So, what we observed is the some data sets are labeled and the plethora, the large amount is unlabeled. Okay, so it was a concept of using the labeled data set to annotate or classify the unlabeled data set, so that this becomes very helpful in certain domains like medical domain and in other domains like financial data. So if we get a sample of the labeled data set, so why not use the unlabeled data set to get a future trend for the upcoming system. So that is why we went with these concepts, and we already semi-supervised feature selection is there, but the algorithms that are there are highly complex, and what we need is non-redundant feature selection methods. And one more important thing that the other feature selection methods missed out was stability. Stability, I mean, how if a feature set has got some feature components, how stable they are, how consistent they are, how many times will they repeat. Was the concept where we stressed. Okay, apart from the concept of semi-supervised version of feature selection. So here we brought out the concept of repeated sample semi-supervised feature selection, that is RSSFS, and this concept uses the concept combination of mutual information and pseudo labeling. And initially, from the data sets, we divided the data sets in the normal way, training and test, and after training, and from the trained data sets, we derived feature sets in different iterations. So in every iterations had got different feature sets, but finally we had to aggregate. We had to come to a common feature set, and that was based on the most relevant and the most non-redundant features. Okay. So where the concept of stability comes in. And in short, this complexity comes to ND, where N is the number of rows and E is the number of columns. So just a snapshot how it works. So normally, now for any data set, we split into train, test, and there was a large portion is unlabeled. So the unlabeled is the largest portion, and the labeled portion is broken into train and test. And after that, uh, using the train set, we apply labels to the unlabeled, and finally the unlabeled becomes pseudo labeled. Okay, and so we at one stage we have these train. After step two, we have the train and the pseudo labeled. And what we do is we augment both this, the train that has got the true labels, and the other that is the pseudo label that is done by us. And together we are creating this augmented set. And the concept of augmented learning that we saw in the title here is the concept of the augmented learning, or the augmented set. Now, if these augmented sets are generated in every iterations, we are running, we run n iterations. So in practical cases, it was close to 100. So from every iterations had got different feature sets, and finally we clubbed this into a master feature set, that is the MFS. And from the master feature set, we got the final feature set. So that is in step 5. So how we got it? It was based on The most relevant and the non-redundant, here we use the concept of the most occurring component in every feature set. Let's say a feature component is occurring more than once, so we use the frequency count of every feature set, and we sort it out in decreasing order, and based on that we arrived in the final feature set. This is just a snapshot of the algorithm that we used. Uh, the complexity was coming to ND, where N is the number of samples and D is the number of attributes. And for finding the feature set for every feature set, it is the complexity of big O of ND. So finally, the complexity comes to big O of ND. Now here what we used is we have used a combination of 18 datasets, and we what we did is, since the datasets are of different types based on the features, or so we clubbed similar datasets into a group, because we wanted to see how our algorithm changes from one size to another size. Okay, does it perform with a smaller dataset, or does the performance can go down in datasets having large number of columns. So that is why we clubbed similar datasets in group A. Some datasets having large number of features in group B, and those that have got more number of columns in group C. So that is how divide into groups, so that to just see the performance of the algorithm. Okay. And here for the simulation, we have used as I said, the unlabeled was the maximum portion, that is only 50%, and the training was 30, and test was 20. Now our algorithm, to just test our algorithm, we have tested against both algorithms. That is the supervised feature selection algorithm, that is got that where the feature sets were derived using only the labeled portion of the data. And the benchmark and benchmark was where your data set had all the attributes or all the features. Now what we chose is, for feature selection we use a certain ratio, that was k, k percentage. So the value was k, the value of k was 20%. That means we have tested with 20% of our features again, that is 20% of the features selected by our algorithm RSSFS, against 20% features of SFS, that is supervised feature selection, against the benchmark having all the feature sets. Okay. So that is how it stands. Okay. So our algorithm had 20% of the top features. The supervised feature selection had 20% top features, but it was based on two labels. Our algorithm was based on the augmented learning, and the benchmark had performed on the 100% of the features. Okay, and see, you can see the performance in group A, in the average. It is benchmark is coming around. If you see the F1 score, it is around 73. We're having the all features, and ours is 73.51, a bit lower than the benchmark. But if it has excelled against the SFS, 71.86. Okay. Same story in group B, right? So in group B, our was 85.67, benchmark was 83.75, and it has again excelled on the supervised features selection algorithm. Okay, so here is just the snapshot as we divided our data sets, 18 data sets in three categories. So how did our algorithm perform against the benchmark and the supervised feature set is the entire story is captured here. You can see here our algorithm, that is the RSSFS, has performed. The yellow one is the model. So it is in group A, it is lower than the benchmark, but it has excelled over the supervised feature selection method. In group B, it has excelled in both the benchmark and the supervised feature selection method, and in group C it is close to the benchmark, but it has excelled over the supervised feature selection method, having all the two labels. And in aggregate, you can see it is close to the benchmark, and but it has in all cases it has always excelled over the supervised feature selection method. Okay, so this was one of the tests that we have done. So whether the test was giving a wrong result or not, for that we have also gone for a t-test. Okay, so and as our sample was less than 30, 18, so that's why we have used it. And what we found is the p value was less than 0.05. So we found that there was a 2.759% of improvement. So that was, now we can rely on it. This statistically significant. Okay. We have, apart from this t-test, we have also performed
Also,
the concept of stability. Yes, from F1 score, we have also checked the stability of the feature sets. So how stable or how similar is the feature set generated by the algorithm against that of the benchmark and the supervised feature set. So here again, the in most of the categories, it is very close to the benchmark, suggesting it has got the feature components are more stable. And apart from that, we have also performed the AUC, that is area under the curve. So here it has again excelled over the supervised feature selection method in both A category A and category C, right? So through this, what finally, if we have to conclude, we have seen that using 20% of the features of the proposed algorithm, we have excelled over the supervised feature set by 2.79%, and over the benchmark having 100% of the features, though by a marginal percentage, that is 0.36. And the similarity of the feature sets among the benchmark and our algorithm was around 40%, whereas the similarity of the feature sets of supervised and our algorithm was 42%. So so it's the components are more or less stable. And in future we think of improving the model, or using this model where the label data is more limited, and if the data sets have some imbalance in the ratio of the class. So that is how we have worked, and we think in future. So that's it from this work.
thank you. Thank you very much. Anybody have any
Thank you.
question?